this little game, but we're not going to actually use cards because it's just easier with the random.org app. But here's the game. You have 5 cards in your hands. 2 of them are aces, 3 of them are kings. The player chooses the first card and then records the result, then the second card without replacement and records the result. If you get 2 cards that are the same, you win. If you don't, you lose. All right? So how are we going to do this in a simulation? That's what we're going to use the generator for, because we need to practice developing a simulation that will model this activity. All right? If we're using a random number generator, how many numbers should we use? 5. How'd you get that? You're right. We have 5 cards, right? You have 5 cards in your hand, right? All right, so of the 5, we need to assign what they are. How many of them are aces? 2. So we're going to use numbers 1 through 5. Numbers 1 and 2 will be aces. That means that 3 through 5 would be what? Kings. All right. Now, we're going to use the random number generator to select 2 numbers. Now we have to ignore repeats. How come? Yes, because it says without replacement, we can't draw the same card twice. So that's how we adjust our simulation for that. We can't use a repeated number. We're going to have it select 2 numbers. We're going to record the results. And determine, determine with an E, if you win. Okay, determine if you win. So on my random generator, I'm going to hit generate. So I have a 3, can't use it twice. 3 to 4. So my first card's a 3, second card's a 4. Well, guess what? That's a king and a king. So I win. All right? So you're going to do the same thing with the generator until we complete the table. Okie dokie? Don't use my data, use your data. Got it? Run a simulation, right, to come up with the probability with our results. So I got 40% chance. Did y'all get? She got 50. Anybody else get higher than 50? Yeah? Really? What'd you get? You got 70? 70? 60? 80? Okay, 60, so nobody got higher than 80. Yeah. So what we did was a simulation, and we based that probability on a simulation, right? That is called empirical. I can spell. Empirical probability. It may not be the true probability, but it's the empirical based on the data of the experiment or simulation. Okay, empirical probability. So what we're going to do is do a tree diagram to find the theoretical, the true probability. All right, so using, ace game. So notice the trees, the branches, all the things. So how many aces do I have? 2 out of how many? So I have 2 out of 5 aces. And then down here is kings. So I have 2 options. Aces or kings. So that means there's 3 out of 5 kings, right? Because in our hand there's 2 aces and 3 kings, right? All right, now After I draw the first card, how many cards are left in my hand? 4. So this next stage of my tree no longer has a denominator of 5, but of 4. So I'm just going to do that real quick. Then we do the first scenario. If I draw an ace first, how many aces are left? 1. If I draw an ace first, how many kings are left? 3. So notice the second card, probability the second card's a king is 3 out of 4 now, right? So I draw a king first. What's the probability that that second card is going to be an ace? 2 out of 4. I drew a king first. How many kings are left? 2 out of the 4 left in my hand are kings. Y'all following me here? A little bit? Maybe? Possibly? Okay. So then it comes down to finding these probabilities. Probability that the first is an ace and the second is a king. Remember, and could be symbolized with the rainbow thing. Okay. So when they do this, when you're using a tree and finding and probabilities, all you're doing is tracing down the branch and multiplying. That's it. So the first is an ace. That probability is 2 out of 5 times the second card being an ace was 1 out of 4, which gives me 2 out of 20. All right. The next one is that the first is an ace and the second is a king. So the first is an ace, still 2 out of 5. But the probability that second card I draw is a king is 3 out of 4, which is what, 6 out of 20? And then we play the other side. Let's say the first card I drew is a king and the second's an ace. So that would be 3 out of 5 times 2 out of 4, which is 6 out of 20. And the first is a king, second's a king. Well, 3 out of 5 times 2 out of 4, 6 out of 20 again, right? Now notice something. What do these fractions add up to be? 20 out of 20. Doesn't that support what we talked about? All the probabilities of a scenario have to add up to 1. They're all right there. We've looked at all scenarios. Now, that being said, find the theoretical probability of winning the game. Well, how can you win the game?
You either get both kings or both aces.
To win, you either have 2 aces or 2 kings, right? And if it's an or, 2 aces or 2 kings. Remember with or, we're just adding. And so what's the probability of getting 2 aces? That would be 2 out of 20 plus 2 kings was 6 out of 20. Oh, why did I write 80? That gives me 12 out of 20. Oh, I'm so having a day. That would be 8, Robin. 8 out of 20, right? Which I guess reduces, doesn't it, to 2 out of 5? 2 out of 5? All right, now then what's the probability that the first card was a king given that the person won the game? So let's practice how we'd write that. Probability, the first is a king, given is that vertical line, there's a win in the game. Now, didn't we on this one right here, we found the probability of winning? All right, so I want you to look at your chart. Right above, on the front of the chart, right above the big black box, there's a Roman numeral 2, and it says probability and distribution. The right-hand formula is your conditional probability formula. Okay? It says probability of A given B is equal to probability of A and B over probability of B. Do you see it? So we're going to use that in this scenario. We would say the probability, the and version, the first is a king and we won, divided by the probability of a win. Okay, so go back to our tree diagram. What did we find is the probability that the first card is a king and we won?
6 out of 20.
Yep, first card's a king, and we win would have to be this one, 6 out of 20, right? Okay, so it's 6 out of 20. Don't freak out because we're doing fractions on fractions. We don't normally do this. It's okay. We can handle it. And what did we say was the probability of a win? 8 out of 20. How do you divide fractions? Do you remember?
Keep, change, flip.
Good. It's just keep, change, flip, peeps. It's okay. So we do 6 out of 20 times 20 out of 8. Guess what? The 20s cancel. 6 out of 8 will reduce nicely to 3/4 or 0.75. Okay. Now, we could not just pick this value off the tree because there's more than one way to win, right? More than one way to win. And that's normally how they ask these questions. When there's more than one way to win or more than one way to get the certain outcome, you follow the branch in the numerator and then you follow the branch twice in the denominator and add them up. Okay? So you'll do lots of these on practice, don't worry. So let's flip it over. General multiplication rule. This is on, it's on your chart. It's just kind of hidden in there. It comes from this formula. I'm just going to write it up here and show you what they did. Probability of A given B is probability of A and B over probability of B, right? So all they did was algebraically rearrange to solve for the and. So if I algebraically rearrange to solve for and, I now have the probability of A given B times the probability of B, right? Just using rules of algebra and solving, that's how you can do it. This is the general multiplication rule. It's not necessarily something you need to memorize because you have the formula, and as long as you know algebra, you can manipulate it, move it around, all right? So the multiplication rule for independent. If A and B are independent, probability of B given A I'll get the symbols right too. If they're independent, then we said this Friday, it's the probability of just B. We take the condition off, condition being A in this case. If they are independent, then you know that the probability of A and B can be found by just doing the probability of A times the probability of B. Okay, why would I use this? Well, it's going to come in handy in some of these scenarios that you're about to see. And here's a hint for you. You're going to use exponents to your advantage when they're independent because that means you would just be multiplying them together a bunch of times. Okay? And then a little trick of the trade. When you're asked the question, the probability of at least one fill in the blank, whatever. The best way to handle that is the 1 minus the probability of none. Because what if they say at least 1 out of 1,000 people? You don't want to multiply 999, do you? No, nobody wants to. It's just easier to do probability of 0 and subtract it from 1. All right, you'll see that here in a sec. Now with tree diagrams, this is kind of what we did. We're just going to put the symbols on it. So this is the probability of A, probability of B. Oh, not A, not B, sorry. A, not A. That's what I'm going to call it, not A. So if this is event A, this is event not A. And then once we've done that, we could have event B or C, either way. So this probability that we find right here when we multiply down the chain would be probability of B given A, probability of C given A. Down here is probability of B given not A, probability of C given not A. All right. And then as we multiply down, we get the ands. We have B, or A and B. Probability of A and C. Probability of not A and B. Probability of not A and C. You may never use this again, but there it is. Multiplying down the tree. All right, let's try one of these. All right. In the 2016 election, 30 states went to the Republican candidate, 20 went to the Democratic candidate. Of the 30 states that went Republican, 29 were in the continental U.S. Of the 20 states that went Democratic, 19 were in the continental U.S. One state is selected at random. Okay, when they give you this, like it's kind of a series of things that happen, that's kind of your clue to do a tree diagram. Okay, we've got charts, we've got Venn diagrams now, we've got tree diagrams. All these are strategies for probability, but when you kind of find consecutive events like this, tree diagrams are your go-to. All right, so let's do this. So let's start with the first thing, Republican and Democrat. All right, so they either went Republican or Democrat, right? How many states went Republican? 30 out of 50, right? And that means that 20 out of 50 went Democrat. Then it branches off and says, we're deciding if they're continental or not continental, right? So same two outcomes, continental, not continental U.S. Continental, not continental. And then what does this say? Let's dig in. Okay, of the 30 that went Republican, 29 were continental. 29 out of 50. Or no, 30, right? So then how many of them are non-continental? 1. Of the 20 states that went Democratic, 19 out of 20 were continental. That means 1 out of the 20 were non-continental. Okay? So there's our diagram, and we're going to use that to find whatever they ask us here. Find the probability that a randomly selected state in the continental U.S. is in the continental U.S. and went Republican. So this is an and. Ands are easy. Ands are just straight down the chain. Okay? So the probability, continental and Republican. Well, how would I do that? I would just read straight down the Republican chain that goes Republican and continental. So 30 out of 50 times 29 out of 30, which simplifies nicely, doesn't it, to 29 out of 50. Which this is where you might want to start doing decimals because it's a little easier than having to deal with all the fractions at the end. So that comes out to 0.58. Now, if we select 4 states at random with replacement, what's the probability we keep it with replacement so that they're independent, okay? So that those probabilities aren't changing because we're taking one out. What's the probability that at least one of the states in the continental U.S. went Republican? One of the states, at least one. So this is using that rule of thumb. Probability of at least 1. Remember, is 1 minus the probability of none. Okay, so we're talking about 4 states at random. So we found up here that the probability that they were in the continental U.S. and Republican is 0.58, right? So then what's the probability that they were not in the continental U.S. and Republican? Yeah, it's just 1 minus this gives me 0.42. That makes sense? Not continental and Republican. Now, it would just be 1 minus 0.42 if we were talking about one state, but we're not talking about one state, remember? We're talking about 4 of them. So I can do it 2 ways. I can say 1 minus 0.42 times 0.42, each one of these representing a state. Or, and what you're probably going to choose is to do 0.42 to the 4th power. It's the same thing, right? And again, you're going to want to use decimals on this. So 969 is what that comes out to be. All right. Given that a randomly selected state is not in the continental U.S., so this is the given, so not continental, what's the probability that they went Republican? Okay, not continental is my condition. So using our formula, that means I need to find the probability of Republican and not continental, and divide it by the probability that they're not continental. So let's look at our chart here, okay? Republican and not continental. Well, Republican and not continental brought me right here, didn't it? 1 out of 30. So that's 1 out of 30 over, well, probability of not continental. We have 2 ways that can happen, right? Republican and Democrat. So that would be the sum of 1 out of 30 plus 1 out of 20, wouldn't it? Yeah. Which is kind of gross, but we can do this. 1 out of 30, common denominator be what? 60. It all comes out to 0.5. I'll save you the math there. It comes out to 0.5. Trust. Don't believe me?
Where'd you get the 2 and 3?
Common denominator.
Oh.
Common denominator is 60. I had to multiply the first one by a 2, second one by a 3. You with me? Okie dokie? Clear as mud?